Welcome everyone. Let's do some combustion reactions. These are my absolute favorite to predict and balance. I find them very fun to do on paper. So we're going to limit our discussion to just complete combustions of just hydrocarbons or anything containing CH or maybe O as well. We're not going to cover other combustions like of metals or stuff because that falls more into combination reactions in my opinion. So we'll just limit it here. Complete combustion means you're going to make carbon dioxide and water vapor. Okay, so we'll just stick with these two simple products. We're not going to be talking about incomplete combustions where you might be making some carbon monoxide or some soot. Or if you have pyrolysis, you'd be making mostly soot or only soot. So let's just focus right here. All right, so I got 4 examples for today in this sort of order. We'll start with a more straightforward example with propane. Then we'll have butane. This will probably be the hardest example today. It's going to require that multiply by 2 step. And then we'll close with burning some sugars, glucose and then sucrose. I thought those examples would be good because there's oxygens in that product with the carbons and the hydrogens. All right, so how to balance? 3 steps. First, do your carbons and hydrogens. And then, this is the important one, do your oxygen last. Okay, oxygen last, oxygen last. And more specifically, we're going to balance the oxygens or add up the oxygens in the products first. Okay, so you'll see this through example today. All right, C, H, and O in that order. All right, example time. So here we have C3H8 propane. We're reacting it with oxygen, and we're going to make our product. So when it's combustion, you always look for your fuel. It's going to have at least carbon and or hydrogen, maybe some oxygen. And then you're going to be looking for oxygen as your reactant. And oxygen is a gas. And since in Chem 101, we traditionally limit it to complete combustion, that means you can predict your products, which is important if they don't provide you the products. Right? So that's always going to be CO2 and H2O as your products. All right, I teach my students to write H2O as a gas because when you do the combustion, it's hot enough that the water will be a gas. I do realize eventually water will cool down and become a liquid. So some teach an L here instead of a G, just so that you're aware of that. But I'm going to be using a G throughout the video here. All right, so let's balance the carbons, hydrogens, and oxygens. So what I like to do is I like to get my carbons done first, and I'll do carbons first. Since I have 3 carbons here, in order to have 3 carbons on the other side, I put a 3 right there to get that equal. If you like to keep track of your elements as you go throughout, right now I have 3 carbons on the left, 3 carbons on the right. This is optional kind of scratch work. I get asked very often, do I have to do this in the middle? No. If you don't find it helpful, don't do it. All right. I have 8 hydrogens on the left, so to get 8 hydrogens on the right, I'll put a 4 right there. So keeping scrap. I can't words today. Keeping track of score, 8H, 8 hydrogens. There we go. All right, now here comes the important part, the part where I feel it's going to be easy if you do it right. If you don't do it right, I feel like it's easy to complicate this. So here's what I mean by do the oxygens on the product side first, the right side first. See, we got something to our advantage here. The advantage here is that we have oxygen on the left as an isolated element. So that means we're just going to count whatever oxygens we have here, and then we'll just choose whatever number in front with oxygen all isolated to make it equal to the right. So I'm hoping I can convince you this makes the math easier. All right, so let's keep track of oxygen. So on the right, so we got 3 times 2 for the carbon dioxide oxygens, and then we have 4 times 1 for the water. All right, so that's going to be subtotals of 6 and of 4, and that's going to be equal to 10 oxygens on the right side. All right, and so to get 10 on the left, since oxygen comes in packages of 2, I'm going to put a 5 here. 5 times 2 would be 10. So I got 3 carbons, 8 hydrogens, and 10 oxygens. And this reaction is done. If you get lost tracking the elements left and right side, I encourage you to draw some pictures. Here, let me pause, and then I'll show you my picture. All right, so here's my picture starting out. So here's our C3H8 propane molecule. What I've done is I put carbons in black, hydrogens in blue. You can see I have 3 carbons and 8 hydrogens. I have 5 oxygen molecules, and they come in packages of 2. If you've studied bonding, you would know that dioxygen has a double bond. If you haven't studied bonding, don't worry too much about this double bond. But yeah, come in packages of 2. So there's 1, 2, 3, 4, 5. That number, right? So that's a 1. We don't write the 1, but it's there. 1 propane, 5 dioxygen molecules, and then so that means like we have 3 carbons, 8 hydrogens, and 10 total individual oxygen atoms. So the important thing in a balanced equation, it should come out to the exactly same totals on the other side. So let's make those pictures. I'll just keep the film running here. 3 carbon dioxides. And then we're going to have 4 waters. Let me do my carbon dioxides first. All right, like in an atoms first class, that's how I teach 101 these days. You would know that carbon dioxide is a linear molecule with double bonds here. And I haven't done the lone pairs. I know I'll get a comment about that. Fine. Lone pairs. Lone pairs, they're important, but sometimes it feels like busy work when you know they're there. All right, I got 3 carbon dioxides, but of course, whereas here all my oxygens were in the molecular elemental oxygen, here on my product side, it's been split up between the 2 different types of products. So let me draw my waters, just finish this up. All right, well, I got 4 waters. Waters are bent molecules. All right, and there's my 4 waters. 1, 2, 3, 4, that 4 over there. And now you can see on the other side, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 oxygens. So the 10 oxygens we started out with, they've now been distributed into these products. The 3 carbons we started out with are distributed in the carbon dioxide. And the 8 hydrogens we started out with are now all in the waters. So every atom has a story from start to finish. Okay, so I thought I'd just show that. I'm not going to do that for every reaction, but I thought it'd be nice for one of them. All right, now example 2. This might be the most important example of the video. So I promised you that this would involve more work, this so-called multiply by 2 step. So I want to show that in action. Let's just first pretend we didn't see that coming, and we're just going to do this reaction as normal. All right, so we see the hydrocarbon here, we see the oxygen, and you're told it's complete combustion. So you put in your carbon dioxide and water gaseous products if they weren't put there already for you. All right, and then now we're going to count carbons. We want 4 on each side. So for me personally, rather than like writing a 1 here and then writing a 4 there and then changing it into a 4, I like to just start with that 4 immediately. For me, that's just a little bit cleaner. And then same thing with the hydrogens. I know I have 10 on the left, so I'm just going to put a 5 right here immediately to get it to a 10. All right, now let's get into oxygens. All right, sometimes I like to write oxy instead of oxygen so it doesn't look like a 0 or something. All right, so 4 times 2, we have 8 from 4 times 2. And then we have 5 times 1 is going to be 5, so we have a subtotal of 13. All right, so far so good. Now you look at this, you're like, I need to get 13 oxygens on this side. What number times 2 equals 13? You're like, well, I don't know. So some thoughts are like this. You try to find a number, and then you're like, let's see, could I put a 6 here? But that would be only 12. Can I put a 7 here? But that'd be 14. So to recap what I've kind of said in my head so far, 6 O2s would be 12 oxygens. 7 O2s would be 14 oxygens. But we need 13. So let me show you a trick. Check this out. Let's choose a number between 6 and 7. Will that give us 13? 6.5 O2s. 6.5 times 2 would give us 13 oxygens. So let's put in that 6.5. Another way you could have thought about that was, well, since this is a 2, I just had to find a number where if I were to multiply by 2, I would get 13. So with a little bit of sense of fractions, 13 over 2 times 2 would also give us that 13. And said one more way, 13 divided by 2 is 6.5. All right, it's the same thing. All right, so and again, if you can normally do fractions in your head and you suddenly have a math panic, sure, just type in a calculator to make sure your math is working all right. All right, cool. So we found the number. Now, most Chem 101 instructors would not accept this as an answer, even though it is mathematically correct. The reason being, most Chem 101 curriculums would say, hey, there's no such thing as a fractional molecule. Like on the earlier page with this reaction, we had 5 O2s. But if we had like 6.5 O2s, we'd have 1, 2, 3, 4, 5, and then we'd have like another one, and then we have like a half of one. But oxygen always comes in packages of 2 under stable conditions. The long story short is, in Chem 101, since most curriculums don't allow for fractions or for decimals, you will have to multiply everything by 2 to remove the fraction or the decimal. And you may be wondering, how did I settle on 2? That's because mathematically that is the denominator of this fraction or that decimal, which means to get rid of it, I multiply by whatever that denominator is. All right. So this is what I like to do when it becomes time to multiply everything by 2. I like to just put a times 2 on everything. And I take the extra time to write it above every single reactant or product, and I turn it into a to-do checklist. In my experience, people sometimes put this out there, and they may forget to distribute it to everything there. All right, so my preference is to write it above each as a to-do list. All right, so let me do that. C4H10. I'll get C4H10 with a 2 in front. Don't write like C8H20. You would change the chemical. That'd be a different, that wouldn't be butane anymore. We're burning butane. All right, 6.5 times 2 is 13. And then 4 times 2 is 8 carbon dioxides, and then 5 times 2 is 10. And now this is what is considered acceptable in most intro chemistry classes. All right, multiply by 2. I'm not going to do it here, but if you're not convinced it's still balanced, I invite you to check the C, H's, and O's on each side. You would get 8 carbons, 20 hydrogens, and 26 oxygens on both sides. All right. All right, we're winding down. 2 more examples left. Let's burn some glucose. All right, if we were doing the burning of glucose on the bench top, we would have it as a solid, but this is can also be done in bloodstreams, dissolved glucose. That would be aqueous. Just keep things simple. I'm just going to stick with one phase label. All right, so usual products. All right. And any of these example problems, I invite you to pause and try it yourself before comparing to my answer and process. All right, here's my solution. 6, 6, 12, 12. Product oxygens first. 6 times 2 is 12. 6 times 1 is 6. That will equal 18. All right, so little bit of a roadblock, just a minor roadblock, which is that this is our first example problem where we have oxygen in the fuel as well. All right, this fuel has already been partially oxidized. Okay, but that's not a worry. We just have to figure out what number times 2 plus 6 is equal to 18. All right, you could write that out algebraically, or you can just kind of do it in your head. It's like, let's see, 6 times 2 is 12 plus 6 is 18, so a 6 would work here. All right, so, and that would be correct. So you would put a 6 there, and then you'd be done. To show that algebraically, that'd be like 6 plus, this subscript of 2 means we're multiplying by 2. We'll say x is our variable, and we need 18 on the other side, so we'll treat that like reaction arrow as like an equal sign. All right, subtract 6 both sides. We get 12 on this side. 2x equals 12. Yeah, that canceled. So 2x equals 12. X equals 12 over 2, which is equal to 6. That 6 is what I put there. All right. So there's your balanced equation for the burning of glucose. All right. Some people consider this unlucky, so we'll just move on to the next problem quickly. Example number 4. All right, similar problem, except instead of a monosaccharide like glucose, this is a disaccharide, a sucrose. This is standard sugar from like cane sugar or beet sugar, pretty standard sweetener sugar. All right, if you know anything about like biology or biochemistry, you're taking any of those sorts of courses, you'll know that. I think this is cool. You'll notice if you compare these formulas, it's not like exactly a multiply by 2. You may notice that like if it had multiplied perfectly by 2, when you have a double sugar, you would have like a 24 and a O12 right there. But it's down 2 hydrogens and 1 oxygen. What happens biochemically is when you have one sugar unit link with another, a water molecule is lost in the process. That's called a condensation reaction. So that's why it's not a typo that it seems to be 1 water molecule short. That is what happens in reality. I thought that was pretty cool. Anyways, not that's relevant for this reaction. So we'll just get back to work here. All right, 12. I need a 12 there. 22. I need a 11 there. You don't see 11s every day in balanced equations. All right, 12 times 2 is 24, plus 11 times 1 is 11. We got 35 here. So 11 plus 2x has to equal 35. 2x equals 35 minus 11 is 24. 24 divided by 2 is 12. So to get 35 here, oops, I'd have to put a 12 there. All right. I did that pretty fast, so let me double check. All right, 12 carbons, 12 carbons. 22 hydrogens, 22 hydrogens. 11 plus, so 12 times 2 is 24. 24 plus 11 is 35. And yeah, we have the same thing here. Yeah, we're good. Okay. All right, so that's some combustion examples. All right. Again, moral of the story, carbons and hydrogens first, save oxygens for last, and count the oxygens in the products first. That makes the reactants beginning left side way easier. Hopefully I pointed at left on the camera. Yeah, I did. All right, hope that helps. Thanks for your attention, and if there's anything you want to see or have explained, let me know in the comments. Thanks, take care.